Uh, Professor Christian Blanchet is going to deliver a talk on the mapping class groups of surfaces acting on non-singular vector fields and related representations. So, welcome to Professor Christian Blanchet in the John Conway Spirit Seminar Series. Over to you now.
Okay, so thank you so much for the invitation and introduction. I like to start with a sentence from Charlie Chin. You can see there is of those who passionately want to know. And I strongly believe that scientific exchanges contribute to peace and human solidarity. And I wish the best to everybody in all countries. So also, I know that there is time for question at the end of the talk, but you are welcome to interrupt either by the chat or direct if you have any question. So let's start seriously with our object. So we are considering oriented surface, genus G oriented surface for business with one boundary component. So it could be extended in many cases, but this will simplify. And I draw here a genus 2 surface. I guess you know elementary thing about this. And here I want to define the mapping class group of sigma. And this means that the set of isotopic classes of diffeomorphism which are identity on the boundary. And these forces, because we have non-empty boundary, these forces that they are oriented. And just for starting motivation, maybe I raise this strong open question. Is this mapping class group a linear group? This means, the question means injective homomorphism from the mapping class group to finite dimensional linear group, or in other terms, is there a finite dimensional full representation? And the answer to this question is known in genus 2, and it was proved by Stephen Bigelow, and it uses a very strong result of the linearity of the classical braid group, which was shown independently by Stephen Bigelow and Dan Kramer. So just have in mind that each time we produce a new finite dimensional representation of mapping class groups, we can ask about the kernel and hope this kernel could be trivial, which would solve this very strong question. So my goal in this talk is to discuss certain representations which are related with action of non-singular vector fields, and introduce a new family of representation we are working on, we are constructing with Awais Shaukat and Martin Palmer. So this will be the very end. I will not give all details for this, but I want to present this new result. So let's speak about, so for those who are not topologists, we are considering here the group of not all diffeomorphism. It's a very smallest group, which is a quotient. So we consider diffeomorphism up to deformation. This is the meaning of isotopic classes. And this group is generated by so-called then twist. So here I will present this then twist. So I represented my surface, and I fix here an embedded curve, and I thicken this curve and get a standard neighborhood of this curve. V gamma is gamma, the neighborhood is V, and this if clearly. And so we define tau gamma. So this will be the then twist associated with gamma. And this then twist is identity outside of V gamma. And in the neighborhood of gamma, it's just given by this very simple equation. So you go across and you rotate left when the time parameter increases. And so, for example, I've represented this neighborhood here. So here is my interval 1, and the circle goes around. And then represented in blue the image of interval times the 1 of S1. And so you see that when you find a curve which crosses gamma, then you turn left and you come back. And it's an old result of then that these then twists give generators for the mapping class groups. And in fact, it was shown by Licorice that a certain finite family of those already generate. There are presentations of mapping class groups. This is very strong topics, and there are many interesting results about this. The scheme, we start a little bit, still introduction, on representation. And I guess you know elementary thing about homology. So if you just know about pi1, just think that homology is H1 in case is just abelianization of pi1. And so it has, in case of a genus of this genus J surface, it has a rank 2G, and it has a symplectic structure given by intersection. So you take with sign elementary intersection of curves, and this induces a symplectic structure. Here I'm working with the integer coefficient. Okay, so you have an homological action. I denote by psi from M of sigma to a subgroup of automorphism of H1, which are composed with automorphism respecting fixing the intersection form. And then it's easy representation. And this representation has a quite big kernel, which is called the Torelli subgroup. And I will Torelli subgroup. So the Torelli subgroup is composed, is formed with those mapping classes which are acting trivially on homology.
Excuse me,
Yeah.
Professor Blanchet. How this action is defined, the homological action?
It's just a bifunctoriality. When you construct homology is a functor, this means that it associates to a topological space. Group, and each time you have a continuous map, then you get between the groups. The homology is a functor. So because mapping class, and in fact, this is homotopical. This only depend on the homotopy class of the continuous map. This means each time. So if you take let's open just a new page. You have oh sorry. Okay, whatever. F from sigma to sigma. This means you will have F star. So if you want to have F sharp associated from pi 1 of sigma to pi 1 of sigma, you just compose. So this means you take gamma, which is a loop, and you go to F composed with gamma. So this is action. And you have F sharp, F star, will be the abelianization of this. And it's something very easy. If you have in your server, you start with, for example, this curve here, denoted by M. I like it to be oriented. So then this means that it represents an element, a cycle, one cycle in H1 of sigma. Okay. And then if you act by F, then you could have, for example, here F of M, which is another homology class. So you will have F star by definition of this homology class equal the homology class represented by M, like this. Sorry, F of no need. The class of F of M. That's quite easy. Is it okay? Okay, so I continue. Okay. So we have this homological action. And in fact, so maybe you have some specific curve which are separating. And when you do the 10 twist along this separating curve, then you will not move the homology. Here, a basis for homology I will represent with blue curves. So I take this curve, let's say A1, B1, they are oriented. Here I will have also E2 and B2. And you see that the then twist along gamma will not touch the AI, BI curve. So 2 gamma will give you an element in the kernel of the mapping class group action. It's an element in the Torelli subgroup.
And what kind of classes will appear in the kernel?
It's written here. So it's a result of Biermann and Powell independently that the Torelli, the kernel of the mapping class group action, this means the Torelli, the subgroup of the surface, is generated by this then twist along separating curve, and also certain bounding pairs generator, which I will describe now. And so this means that everybody in the kernel is composition of those. And or conjugate of those, but the conjugate of those is already, it's another one. So a bounding pair is like this. You take 2 curves, gamma and delta, which together bound a subsurface. This subsurface is here. And then you can compose one then twist along gamma with the reverse twist along delta, and you can prove that this is also an element of the kernel. And this result of Bierman and Powell says that you get generators with those. So you should think that in this kernel, you have a composition of den twist along separating curves, or maybe round pairs like this. In fact, there is even stronger result about generation. You see that a bounding pair has a certain genus corresponding to the bounded surface. Here, this is a bounding pair in genus 1. And it was proved by Johnson that these bounding pairs are enough for generating. Okay, so you have a certain composition of specific den twists. Okay, so this was kind of an introduction to the topics. The surface, the mapping class group, its natural action on homology, and an interesting subgroup, which is the kernel of this action. Okay, now we start with non-singular vector field. And I use Riemannian metric for convenience, but we could avoid this. So in particular, what we will do really doesn't matter of the choice of the Riemannian metric. So then we have a unit tangent bundle. So it's a three-dimensional manifold with a map to the surface and a fiber, which is the circle. And a vector field, I will take a unit vector field. If I start with a non-singular vector field, I'll kind of normalize so that it's unit vector field. And I take homotopy classes of section of this bundle. This means that here you have a projection map, and you want that composed with P is identity sigma. So you take homotopy classes of vector field, unit vector. And in fact, this is a rather simple set. If you take all vector fields, even non-singular, it's rich and complicated, but up to homotopy, you do not have so much. And if you teach or know some elementary geometry, you know about affine space structure. And it happens that affine space of a homology with integer coefficients. And you see that when working in affine, you have the vector associated to this point, which is a difference. And here, this affine structure is given like this. You take two vector fields, and you have a difference in some sense, which lives in H upper of sigma, which is a cohomology class, and it's defined by a rotating number. So if you are, I will draw the best expression with this picture. So here, everything is, and I take to be and then the green vector field Y is following the circle. So it's tangent to the S1 factor. And then when you go along gamma, you count the rotation of the green with respect to the blue. You see from here to here, you rotate 1/4, or pi over 2 if it's an angle. And when you go all around, you just rotate an angle of 2 pi and you count 1. And this is the idea of comparing two vector fields along a curve, and you can show that this gives you a difference in the cohomology, and you get this affine structure. So in fact, once you fix a vector field as base point, as origin, then homotopy vector, non-singular vector field is the same as cohomology, as usual. If you fix a point in a affine space, it becomes a linear space. Okay, questions so far? So this means that we have a nice cohomological interpretation. We can deduce from this. My point is to think about action of mapping class group on vector fields. And it's convenient to have a cohomological interpretation of this space Xi of sigma. And if I take that, I will use here a bit of algebraic topology. You could avoid, but I think it's convenient to see like this. So if I have a vector field, remember that it's a map, it's a section. In particular, it's a map from sigma to T1 of sigma. And then, by the same functoriality argument as before, this means that you will have a map from H2 of sigma come a boundary of sigma, which is equal to Z, and it's generated the so-called fundamental class of sigma. And then you go to H2 of T1 of sigma. And here I'm again using quite basic algebraic topology. I don't know if you are all aware about this, but it's really a basic knowledge in algebraic topology. And you have this Poincaré duality. This means when you have a free two cycle or surface, intersection with this surface will give you a one form. And so this Poincaré duality says, yeah, you will continue and get an element in H1 of the unit tangent bundle.
Excuse me, Professor.
Yes.
By H2, the second level homology, you mean the relative homology with respect to
it's a relative homology with respect to the boundary, unless it would be zero. It's when you have a manifold, oriented manifold with boundary. If it has no boundary, the higher homology is isomorphic to Z, and the orientation gives you the preferred generator. If it has boundary, the higher level homology vanishes, but the relative homology to the boundary still has a fundamental class and is isomorphic to Z. Okay. Yeah. Then you can work a bit and see that if you compose this map and you go from a vector field to this H1 of the unit tangent bundle, then you will get a bijection between homotopy classes of vector field and an affine subspace in H1 of T1 of sigma. So you can realize the vector field as a cohomology class, which is required to evaluate one if I take a differential geometry formulation when you integrate over the fiber. So this means that you have a model, a cohomological model for this space of vector field. And then you can act with the differential of f if you take f is represented by a smooth math, so you have a differential, and the differential is acting contravariantly on the cohomology. And this action induces an action on the subspace, the affine subspace of homotopy vector fields. So you see, I started with non-singular vector field or unit vector field, which is really a very geometric notion. But because I take up to deformation, up to homotopy, I can translate the set of homotopy vector field into certain cohomology, and action on cohomology comes from functoriality of this cohomology.
Excuse me, Professor Blanchet, what do you mean by affine action?
This means that
isometry?
No, it means when you have affine action, you have action by translation. When you have affine space, you have action by translation.
What does it mean? Can you explain it? I didn't understand.
Okay, I can just open still, thank you. So if you have V, which is vector space, with module is the same, but I'm just doing elementary geometry. Let's say a K vector space, whatever it is. And then you take A, which has affine space over V. So this means that V is the associated linear space.
Okay.
And then if you take U in V, then you get, if you want, I denote like with student translation from A to A, and it sends the point A to, you say the translation, and I'd like to write it if you want, A plus U.
Yeah, I got it.
Okay. And this means that by definition of affine space, you get simply V acts simply transitively. It could be a definition on A. In fact, it could be a definition of affine structure. And compatible, I mean, the action commute with this action. The action of the mapping class group commute with translations.
Okay. Thank you very much.
It's before. Okay, so affine action exactly means that it comes with translation. So my question now, I raise this question about orbits in this in vector fields and the action of mapping class group. The mapping class group is acting on vector field. I have the cohomological model for this, and I'm interested in characterization of orbits, how many orbits, and how I can recognize. And in fact, this question is motivated by some work which we want to continue with Haniya Azam. And we constructed with Haniya the topological Fukaya category, but it was a Z/2 graded version. And the Z graded version depends on a vector field, or more exactly on a line field, which is very similar. And our question is, do different choices of the vector field or of the line field produce equivalent category? And so for this question, we are working on, and we need to know answer to this question. And in fact, the the answer is not very complicated, and in fact, you can find it in the literature, but I will explain this.
What do you mean by Z2 graded Z quadrant version?
When you take when you construct this kind of deep gadget, which is called the Fukaya category, you are producing a graded category. This means each object has a certain degree. And you can have either degree in 0 or 1. And this is what I mean by Z2 graded. Z2 is my notation for Z over 2Z. Okay. So when you take a weak theory, it will be only Z over 2Z graded. So you have just even objects and odd objects. But when you take a stronger construction, will involve objects which are graded by all integers. And in this case, you need to make a choice for fixing this Z grading, which is this notion of vector field or Eigen field. Okay.
So this Z2 grading you're going to introduce on the fee structure?
I will not develop this. It's just a motivation. It's just to say that the question I will answer to here is something which will be useful in subsequent work about these Fukaya categories we are doing with Haniya. But I don't want, it's not the purpose to develop this here. Okay, I just say that in this setting, understanding orbits in Xi of sigma is something useful. Is that okay? Okay, so I'll continue. Okay. Okay, so let's start. So for this, I need another gadget, topology or geometry gadget, which is a model. It's a description of spin structures on surfaces, and it's something rather elementary, but probably not so well known. So now I define a certain quadratic function, Z over 2 quadratic function on the homology of sigma. So this Q of sigma, it's a model for spin structures on sigma, and it's a set of maps Q from H1 of sigma with modulo 2 coefficient. So just think you take H1 integer H1 and reduce coefficient mod 2. So it's a Z over 2Z space of dimension 2G. This is H1 over 2. And then I go to Z2, but I do not ask, it's not linear. It sends 0 to 0. And it's the defect of linearity is given by the intersection. So this x point y counts modulo 2, the intersection, the number of intersection points between a curve representing x and a curve representing y. So for example, I will have example afterwards. So it's also rather elementary that this is a affine space of a H upper of C with coefficient over to have the same as before. And for example, if I take genus 1, and if my genus 1 surface has bases for homology AB, then this spin structure is completely determined. So of course, it takes always 0 for 0. A can be sent to 0 or 1. B can be sent to 0 or 1. And then because A dot B equal 1, here you have one intersection points. If you start with 0, 0 and apply this formula, you get 1. If you start with 1, 0, then you get 0. And at the end, if you take 1, 1, then here you will get 1 plus intersection. And so you have here this half invariant, which summarizes the situation. And I like to call it a democratic invariant. So here, this Q0 quadratic form take 3 times. In fact, this in genus 1, the cardinality here of H1 is 4. It's a Z/2 a vector space of dimension 2. So you have 4 elements. And the image takes 3 times 0, 1 times 1. And I will say that the democratic invariant will be 0. They voted, 4 people voted, and 3 voted for 0, 1 voted for 1. So, and you see that you have 4 different spin structures, and 3 times you get democratic invariant 0, and 1 times you get democratic invariant 1. And so this you can define in general. You can prove it's not very deep, that if you take a spin structure in general, the quadratic form like this, then either you take the number of 0 in the image will be 2g minus 1 times 2g plus 1. In genus 1, it was 3. And then the number of 1 in the image is 2g minus 1 times 2g minus, or it will be the converse. You exchange the numbers. You have and the definition of the half invariant, half of Q, is this democratic invariant. The value is 0 if you take more times 0 than 1 with majority. And the proposition is that finally selecting